So hi everyone, my name is Pelayo Peñarroya, and today I will be presenting you my PhD thesis topic, Intelligent Navigation and Control System for Minor Celestial Body Ascent and Descent. Well, first of all, I would like to introduce the frame in which this project has taken place, and this is within the Marie Curie scholarships. These scholarships, which have been promoted lately in our teams and so on, promote specifically three main pillars, right? They provide funding for research because you need some funding, or you should have some funding while you're researching. And also they promote collaborative research, which is very nice. In our project in particular was a specific effort into bringing together the engineering and the more mathematician and physicist kind of world and finding the middle point. So it was a very rich experience in that sense. And then also it's a very good opportunity for career development since, as you will see later, there's a lot of training within the network itself. And then on top of that, you can have training externally, no? But it's a very complete program. And if you have the chance to apply for any of these, it's a difficult process, but I totally recommend it. And I'm very happy with the experience. In particular now, the objectives of my research were to design autonomous landing systems for harsh environments, taking into account high fidelity models, and specifically putting some effort into the resilience, so the robustness of the methodology, right? Due to the large amount of uncertainties that you have in minor celestial bodies. Well, this is a bit of a screenshot of the map that I initially went through, and I have highlighted here, the HDA system, which was the main focus of my work. HDA stands for Hazard Detection and Avoidance Systems, and I will now try to bring or give you some idea about what these systems are about. So this is one of the first examples that we find. This is the ALHAT system that developed by NASA. The idea was to using a LiDAR, which is a light-based radar, let's say, to scan a terrain, and then based on the 3D scan of the terrain, you can compute the roughness, the slope, and then based on some cost function, you identify some safety map, no, with zones where you are able to land or not, depending on your criteria. With that in mind, what I did at the beginning was to plan a roadmap, let's say, for the research with some methodology. First of all, we needed to create a baseline GNC simulator, which we call DastroSim. And then, of course, you need to identify the different key concepts that you think you can use in your research and implement them to see which works better or which you think has a better potential. After that, we assessed the performances of these methods, which brought us some publications. So the roadmap, you see that it's not only planned technically, but also in terms of results and things that you need to produce during your PhD. And finally, we wanted to consolidate the algorithm and hopefully raise the technology readiness level. Well, I have to say that this was the plan, but of course, I think I didn't know that I was going to focus on HDA systems until I was in step 4 or something like this, to be honest. But I think this is also the normal process in research. So Astro HDA is the name of the module that I developed to this actually HDA system. It's composed by 3 layers. As you saw here in the ALHAT project, they have like roughness, slope estimation, and propellant cost, for example. In my case, I focused on shadow detection, feature detection, and slope estimation. We used a ResNet 34 architecture for the network because we're using CNNs as well, as Alfredo was just explaining. It's really nice to have Alfredo talk before me because he always explains all these things and then saves me some time. And the technique in particular is called semantic segmentation. That's the one I'm using. Let's say the innovation of the research, we wanted it to be the use of passive systems as opposed to active systems. For example, LiDARs are active systems because are sensors that are sending some information and then receiving some. Instead, passive systems would be cameras, so you would only use images. For shadow and feature detection, there were some works already, but for slope estimation, it's a very difficult task to obtain three-dimensional information from monocular images in this case, no? So this was a bit of the challenge of the research. And also LiDARs have the disadvantage that are generally large systems that really limit the design of your spacecraft. So for example, having a LiDAR in a CubeSat would not be feasible simply. And this allows a huge plethora of different missions to actually use these systems, which are just you carry a camera, which is something that all systems nowadays carry. So to do that, we also generated we created a data set. We created a pipeline using Blender, and these are some of the images that we are generating. So we have some shape models on top of which we distribute stochastically populations of features to generate a variety of different geometries and configurations. With that, we end up with these three types of images. On the left side, you see the naked image, which is just the shape model. Then in the middle, we have the slope model. We use a threshold in this case, and above this threshold, we consider it safe to land, and below, we don't. So we analyze each of the facelets of the shape model, and we compute the slope at each of the points, and then we obtain this image in the middle that we use as a mask for the training. And then on the right-hand side, you can see how the same naked image has two different feature populations on top of each. On top of each other. On top of them. So you can see how the different features have been distributed to create more variety in the dataset. These are some of the results. On the left-hand side, you would see what the camera would be taking. And then in the middle, you see the results. The first column would be the mask, so the ground truth we are targeting. In the middle, you see the estimation of the network. Very interesting to see that, for example, to label the features, we used an automated method that basically puts a rectangle around the feature, and you see how the network learned to actually estimate more natural shapes. So this was very nice. Then here you see this is the shadow estimation, which in the end looks for gradients in the tone of the image. And then the slope estimation, which is the most challenging one. And very interestingly, you see here on the right-hand side the probability maps for the labeling, because you don't only want to have, let's say, a binary information about whether this is safe or not, but also you are interested in the probability, because maybe you want to fine-tune it to your threshold. No? So this is also a very nice feature to have. And you see that, of course, the slope estimation is usually the most challenging. Indeed, what we see here is that we don't get all of the very, very minor red dots here, but we get the main geometry of the slope, or the main characteristics of the slope, let's say, which is very good news. And then in the end, what we do is we overlap each of these three estimations, and we get to the image on the right-hand side, which is a safety map with all of these layers composed. Then we had a secondment at the FKI in Bremen, where we also mounted this algorithm, or let's say we loaded this algorithm into a Raspberry Pi, and we used a camera module, because some, for example, CubeSat missions use this kind of processors, typically university missions and so on, and we wanted to test it in a very low condition environment. And we took some images with different illumination conditions, different clustering techniques, and so on. And the algorithm performed quite well. There's, of course, always room for improvement, but for the time we were there, we were really happy with the results, and this brings a bit the TRL higher of the technology we developed, so we're very happy with the experiment. Then in terms of publishing objectives, we managed to publish the simulator in AstroSim, and then the HTA, we also published it, the Astro HTA, we also published it in Celestial Mechanics and Dynamics Astronomy. Now we are working on a third project together with Thomas and Alfredo, two colleagues. Alfredo just presented, and Thomas is another colleague. And the idea is to focus on the methodology of having a fully autonomous GNC, let's say, loop, where we basically have an image as an input, and then combining Alfredo's relative positioning network with my hazard detection and avoidance network. What we do is we basically have this safety map, and combined with the position where you're at, you perform some ray tracing, which basically converts pixel to body coordinate. And then the idea is to create a safety map of the global satellite. So basically, in this case, I'm representing a case where we are orbiting the Bennu in a polar orbit. You see the trajectory like this because it's represented in body fixed coordinates. And what you would see is you take this image, you generate this map, and with Alfredo's information and this pixel, this ray tracing technique, you would project this map onto the surface of the body. So after taking some images during your surveillance orbit, basically what you get is a fully a global safety map of the asteroid, and once you got this map, you have to select the point that suits your landing criteria better or best, and then you're set. These are all the training activities that we had during the Stardust program. These are only the internal ones, so you have also external ones, but there are a lot, and they are super good opportunities with very high-level professionals, and I personally learned a lot from them. You also have some outreach activities, which are fun. Depends on how you are, if you prefer to do them or not. I personally like them a lot, especially going to schools and so on. I think it's very interesting, and actually you learn a lot also from the questions of the children, and it's fun in the end. Well, these are some of the references I used during the presentation, and that's it. I think I don't have time for more. So thanks.